Welcome back, and we are now on the last part of the NMOS 2021. We're going through the last 10 questions, which are supposedly the most difficult 10. As you will see, some of them are really quite challenging, but there are also a few that seem a little misplaced. And that's something that's pretty important, because you shouldn't start and end at 1 to 20 and say that the last 10 are definitely too hard for me. There's a good chance that a few of them are difficult only in the perspective of the question setter, but you might not find them very difficult at all. So do try every single question, at least read it and consider whether you have a clever idea for how to approach it. I mentioned at the start of the first video that the last 10 questions you should budget about 40 minutes for yourself. I don't think this video will go up to 40 minutes. However, you should still try to take it at a pace where you're comfortable. So feel free to pause the video for a while if you need to digest some of the ideas. Alright, so let's jump into question 21. This Alphametic where there are A, B, and C, and it is a subtraction. Now straight away, you see that there's an A and it became a B. So you know that it must have been a case where you borrowed 1 from here and there is a 10. So A minus 1 must have been equal to B since A and B are different. Okay, this is something that you can use as an equation, or just think of it mentally as A is 1 bigger than B. Now this is important because if you were to look at the ones digit now, the ones digit tells you that B minus A gives you C. Well, B is 1 smaller than A. So you wouldn't be able to subtract because it's smaller. You must also have borrowed from the A in the tens place and got an extra 10. So B is 1 smaller than A, but you give 10 to it, so 10 plus B is 9 bigger than A. So therefore, C should be equal to 9, which we can happily write down here. This is 9 and 9. Now let's look again at another B minus A, but in this column, the hundreds place. Now in B minus A, with a carryover of 10, we saw that it was 9 in the ones place. Here the B minus A with the 10 carried over from here does not seem to give you 9, it gives you a different digit, it gives you 8. So what could be different here? Well, the only way it could be different is that you also borrowed from B, meaning that you borrowed a 1 from here, so it's actually B minus 1 and a 10 came over here. So therefore, this is actually not 10 plus B, this is 10 plus B minus Y, which is 9 plus B. Since B is 1 smaller than A, if you give it 9, then that becomes 8 bigger than A. So 8 plus A minus A gives you 8. And here it says 8. So that implies that A must be 8. And if A is 8, then B is 1 less than A, so B must be 7. Okay, so here we get 8787 minus 898 is 7889. And the 3-digit number ABC is 879. Pretty nice question actually, because it just uses the properties of subtraction. You don't need to do any guess and check. Question 22, oh, that's long. A bag is filled with blue and red balls. At first, Audi draws 30 balls randomly from the bag and finds that 27 of them are red. Okay, so at first you get 27 red and 3 blue. I'm not sure what's coming next, but I just write that down since that's obvious. He did not replace these balls into the bag. Thereafter, he will draw several rounds of 9 balls randomly without replacement, until the bag is empty. After each round, he realizes that exactly 5 of the 9 balls drawn in that round are red. Okay, this is extremely coincidental. It says that 5 out of 9 are red. So you basically have 5 red, 4 blue, times a lot, right? It says after each round, so each round happens to always give you this. And the total number of red balls that have been drawn so far from the beginning up to that round is always maintained at least 60% of the total number of balls drawn so far. Okay, this is interesting. Now, why is this interesting? Because you see, this is 5 out of 9. 5 out of 9 is less than 60%, because 60% of 9 is 5.4. So 5 out of 9 is less than 60%, meaning that if you keep doing 5 out of 9, 5 out of 9, 5 out of 9, you are eventually going to drop lower and lower and lower until you go below 60%. Now, the reason why it isn't immediately less than 60% is because you kind of got a head start. The head start is that 27 out of 30 are red. So at first you have 90% red, and then you kind of dilute it, and then eventually it goes past the 60% to 50 something. Well, eventually it would, but it says that it is always maintained at least 60%. So given that there are no leftover balls in the bag after the last round, what's the maximum number of balls in the bag at the beginning? Okay, so let's read this carefully again. It says that the total number of red balls that have been drawn from the beginning up till that round is always maintained. So including the last round, right? Because it says after each round, so that means at the end. Now the percentage will keep dropping down because you start at 90 and then you keep diluting it, right? So the always maintained at least 60, we can just treat it as at the end. At the end. And let's say that at the end, how many are there? Well, I don't know. It depends on how many rounds there are. And how many rounds there are would tell us how many balls there are in the bag at the beginning. Okay, that's a tongue twister. Balls in the bag at the beginning. Well, let's call the number of sets 1 unit. And so at the end, the red balls would be 27 plus 5 units. The blue would be 3 plus 4 units. I need to make sure that the red balls are at least 60%. Now, at least 60% means at least 3/5 of the total. And I think an easier way to deal with that would be to say that this ratio is more than 3:2, because 3:2 would be 60% and 40%. And so the red proportion is more than that, means that the ratio is more than 3:2. And I can write this as a fraction, just because it's a bit weird to write a ratio vertically down. Okay, now here, 27 plus 5 units is over 3 plus 4 units is more than 3/2. We can cross multiply. So 2 times 27 plus 5 units is more than 3 times 3 plus 4 units. 2 times 27 is 54, plus 2 times 5, which is 10 units, is more than 3 times 3, which is 9, and then 3 times 4 is 12 units. So 54 plus 10 units is more than 9 plus 12 units. I can minus off 10 units from both sides, and then I can minus 9. And so 1 unit is at most 22, right? Because 22 times 2 is 44. So this 1 unit is at most 22, and I cannot have a fraction since it says there are no leftover balls after the last round. So it is a perfect number of sets, whole number of sets. So at most 22, and so that would correspond to 22 sets of 9 balls, 5 plus 4, and then the initial 30 were also in the bag. Okay, so 22 times 9 is 198, 198 plus 30 is 228. So this is the maximum number that could have been there at the beginning. Now expect 1 or 2 of these kinds of word problems every time. They may be a little bit intimidating looking, but if you have time, it is a good question to do because the idea is usually very similar no matter what the context is, whether it's balls, it be marbles, it be pencils and pens, it be cats and dogs. It's always going to be pretty similar. But if you're left with 2 or 3 minutes, this is probably not the question to do, because just understanding the question may already take you that long. Okay, next is question 23. This one's a little odd. Now, I do have some idea of what the question setter is trying to do here, but I don't think there's any point in doing anything more clever than just adding fractions, you know. Well, 4 fractions here is not going to be that messy, so for 3 marks, it's totally worth it. Now, I'll look at the two that seem very juicy. 1 over 8 and 1 over 24 look like they are easy to add, so we'll start with that. The common denominator is 24, so 3 over 24 plus 1 over 24 is 4 over 24, which is 1 over 6. Well, what do you know? That was nice. Now, I can also add the other two now, 1 over 15 and 1 over 35, because they have a common factor of 5. So this is 3 times 5, this is 7 times 5, so I need to have a common denominator of 3 times 5 times 7. That is 105. The first one's missing a 7, this one's missing a 3, so 10 over 105, there's a common factor of 5, which I can cancel off. It is 2 over 21. Well, 2 more to add up. 1 over 6 plus 2 over 21. This has a common denominator of 42. 7 plus 4 is 11 over 42. Great. So this is 11 and 11. So I know that when I have 11 divided by this fraction, it is just 11 times the reciprocal, which is when you flip it around. Right? This is how fractions work. When you divide by a fraction, it's the same as you multiply by the reverse, the reciprocal. So 11 cancels out and your answer is 42. This is a very, very value for money and value for time, 3 marks to get. 24. The figure below shows a regular pentagon. Regular is important because it means all the sides are equal and all the angles are equal. The lines AC and BD intersect at the point F. Given that CFD equals to x, find the x degrees, find the value of x. Okay, this is interesting because if you notice, this is a line of symmetry. Right, so everything over here would be symmetric. If you can find one angle, you can keep flipping it over. And there's another thing which I can use to get some angles around this. Right? I can use the fact that I have some, well, I have many, but I have some isosceles triangles that are hovering around this angle x. So, in a regular pentagon, we know what is the angle sum. We know that the angle sum, since a pentagon has 5 sides, it is 5 minus 2 times 180, which is 540 degrees. So that's the angle sum, and so each angle you would divide that by 5. 540 divided by 5 is 108 degrees. So I'm going to put that here. Since that's the one I highlighted, I can find the 2 other equal angles in my isosceles triangle. Right? These 2 are equal, so 180 minus 108 divided by 2 is 36 degrees. So I'm going to write that down. This is 36 and 36. And one more thing is the line of symmetry that I wrote just now. Yes, that is useful because since this is symmetric, this angle down here, BCA, will also be equal to CBD, which is 36 degrees too. So X is the exterior angle of triangle BCF, and that would be 2 times of your, okay, let me highlight it properly. Yeah, this triangle here, X is the exterior angle of that. So it is 2 times of 36 degrees. which is already your answer. So this is a pretty good illustration of what you do when they tell you something's regular. Regular means that you have equal angles, you have equal lengths, and you have lines of symmetry. So we use the equal angles to find the 108 degrees. We use the equal lengths to get the isosceles triangle with 36 and 36. And we use the line of symmetry to get one more angle of 36 degrees. Right? So these are all the three things you can do with regular polygons: equal sides, equal angles, and lines of symmetry. On to question 25. Let n be equal to 2 to the power of 2021 plus 2021 squared. Find the remainder when n is divided by 7. Now, you know what this kind of question is? This kind of question is a reward for hard work. What do I mean by that? I don't mean the hard work of calculating 2 to the power of 2021. That's not hard work, that is just a waste of time. The hard work that comes before the competitions, because these sorts of questions recur so much that if you have never tried any practice, you would have no idea how to do this, and if you have, this would be quite a familiar question. Hopefully after watching this video, it will be a familiar question to you as well if you haven't already seen it before. Now here's the idea. First of all, we are not going to deal with these at the same time, right? 2 to the 2021 and 2021 squared can be separated out. So I can find the remainders of each part and put them together. Right? So let's say that if the remainder here was, let's say, 5, and the remainder here was 3, let's say. Right? So the remainder 5, remainder 3 means that you have 5 left over, 3 left over, you put together, you get 8 left over, but 8 is not the remainder. From the 8, you can take 7 more out, so the remainder would be 1. Right? So I can just look for the remainder of each of these parts on their own. Now let's do the one on the left first. The one on the left, 2 to the power of 2021, there is a very simple way to do these sorts of, find these sorts of remainders when you have a power. And that is to just find a pattern for your powers and the remainders. So 2 is just 2, 2 squared is 4, 2 cubed is 8, which 8 divided by 7 remainder is 1, 2 to the power of 4. Now the trick is that you don't need to calculate out the whole thing. You just take the previous one and multiply by 2. So you don't need to take 8, you can take 1 and you can multiply that by 2. Okay, and then after that, 2 to the 5 is 2 times 2, which is 4. And you see it repeating, right? 2, 4, 8, 2, 4, 1, 2, 4, and then you times 2, it will be 1 again, and so on. So it repeats every 3 steps, and 2021, I can divide that by 3 to find out where in this pattern it appears. So 2021 divided by 3, you can use the divisibility test for that to save you a bit of time. 2 plus 2 plus 1 is 5. 5 plus 3, the remainder is 2. So it would be the second number in the sequence, which is 4. So the remainder from this first part is 4. Okay, now let's deal with the other half of it, 2021 squared. Now, first of all, this one is not a pattern of writing down the powers. It's a pattern of writing down squares. Right? So 1 squared, the remainder is 1. 2 squared is 4. 3 squared is 9, which gives you 2. 4 squared is 16, which divided by 7 is also 2. 5 squared is 25, which gives you a remainder of 4. 6 squared is 36, divided by 7, remainder is 1. 7 squared, of course, is divisible by 7, so remainder is 0. 8 squared, so once you have reached 1 to 7, it's going to repeat again. Right? This is how it works, because when you go 7 more, then everything is going to be repeated in terms of the remainders. Right? So it will repeat after 1 to 7. If you think about this, you realize that, didn't you just waste your time writing this out? Yes, you didn't need to write this out. I just wanted to show you the beginnings of the cycle, right? Which is that after you reach past 7, it will repeat again. So all you need to do is to figure out where does 2021 appear in this pattern, and this time you take 2021 divided by 7. There's no shortcut for that. You just do your normal long division, and if you did that correctly, you would get a remainder of 5, which puts you into this box, and in this box you get 4 as your remainder as well. So it is 4 and 4. Okay, so 4 plus 4 is 8, and like what I explained just now, 8 is not the remainder. You can take away another 7, and your remainder would be 1. So this same idea works, and you don't need to write down this whole table once you're comfortable, right? You could just write down 2, 4, 1, 2, 4, 1, just multiply by 2 every time on the left. And for the one on the right, you could have just done 2021 divided by 7 to get the remainder of 5, and then done 5 squared gives you 25, which has remainder 4. So really, you could have saved a lot of steps, but I hope this more detailed explanation helps you understand what's happening. Okay, onward to question 26. Shown below is a right-angled triangle ABC with angle ACB equals to 90 degrees. DEF lie on the sides BC, AC, and AB respectively, such that BDEF is a parallelogram with an area 153 cm squared. Given that DC equals to 9 cm, find the length of AE in cm. This is interesting. So I have a parallelogram. Let's just mark that out. Okay, so I know that for parallelogram, if they gave me area, the area of a parallelogram is the base times the height. So the height is CE. I'm just going to highlight that. So the height of your parallelogram would be CE, and the base of your parallelogram would be BD, or perhaps EF. I mean, they are equal. You could use either of them. So I'll write them down first, so that I know what exactly is the, still didn't highlight them. What exactly are the two things which are being multiplied to give 153. Now the interesting thing is that seems to have nothing to do with the 9 cm, right? And it also seems to have nothing to do with AE. So I have to use something else. I think what we can use is a very common trick when you are dealing with any products of lengths. You want to relate that to ratios of sides. And when you have ratios, you can cross multiply to give you multiplication. So what I'm going to do here is to highlight a pair of similar triangles. Now, similar triangles are triangles that have the same shape but have a different size. Right? So here, well, there's a horrible drawing, sorry, but yeah, here and here. Maybe I'll redraw the one on top. Right, so I want to say that these two are similar to each other. Now, what's the rule for similar triangles? The rule is that they must have the same angles, and then the sides will be in the same ratio, right? It's just like zooming in and zooming out. So because of the parallel lines, I know that these are both right angles, and because of your alternate angles, this is equal to this is equal to this. And yeah, I don't need to mark the last one because that would be just corresponding angles. Fine, I'll just mark it anyway to show that all three of them are equal to one another. So I want to write down some ratio that is relevant. What I will write down when I say relevant is to use the things that are given, the things that I want, and the things that are related to the information. So AE is definitely relevant. And so one of the ratios would be AE is to EC, right? So AE to EC is the scale factor, right? How many times did you zoom in to make your AEF? Now the other one that I want to use is the thing that I know. So AE is to EC would be EF over DC. Right? Again, EF and DC should be in that same ratio because it's just the same shape. Now, if you cross multiply, it means that EC times EF equals to AE times DC. And most of this is actually nice because EC times FE is here. Right? This is 153. AE is the thing I want. And DC is 9. So AE is just 153 divided by 9. Well, this is really clever. Okay, so remember, when you see a multiplication in your area, sometimes you can't use ratio of areas here. Try to get ratios in a different way, right? Because there's no other area anywhere. You can use ratios coming from similar triangles. And similar triangles always come when you have parallel lines, because parallel lines give you equal angles, and equal angles give you shapes that are basically the same, just with different sizes. We call those similar triangles. Okay, 27. In a 2x2 square grid, a random straight line will pass through at most 3 grid squares, as shown in figure 1. Okay, so it's saying that you cannot draw a line that goes through all 4, because you can't draw a line that bends like that. That's not a straight line. It says through the square, it means that you cannot draw it through the middle and say that's everything. Right? You cannot draw it through the center and say that, oh, this center is all 4. No, the center doesn't count. In a 3x3 square grid, a random straight line will pass through at most 5 grid squares. Okay, so let's just sort of highlight the squares to see where they are at. So these 3 squares are passed through by the line. This one is these 5 squares are passed through by the line. Find the maximum number of grid squares that a random straight line will pass through in a 10x10 square grid. Now, perhaps some of you already can sense that there's some sort of pattern, but whether you see a pattern or not, 3, 5 is not a pattern. You need to at least draw 1 or 2 more in order to get there. Now, don't draw a 10x10 grid. The reason is that there is no way you're going to draw it perfectly to scale unless you spend 10 minutes measuring everything and spacing it out really nicely. So draw a 4x4 grid first, and if you can find the pattern, you don't even need to draw the 10x10 grid. So let's try to draw a 4x4 grid. I'm doing this without a ruler, so hopefully it doesn't look too bad. Okay, so you have this 4x4 grid, and let's say I want to draw a straight line. Now, I could draw it something like, if I just went straight through, that's not very good. I would want to slant it so that it passes through things for across, like a diagonal. Now, if I drew something like this, let's say here, I get 1, 2, 3, 4, 5. I don't think that's the best because I already did well with 5 for the 3x3. So I think we can use something similar then. Let's just draw it like across like this. Okay, so this would go through 1, 2, 3, 4, 5, 6, 7. And you realize that this is that same staircase shape that we got for figure 2. Now, it's actually quite intuitive that we can't do better, right? We can't do better because you won't be able to U-turn back in your straight line, right? Your line can only keep going down in that same direction. Of course, it could go up instead of down, but that's just about whether you flip it over, and we don't need to worry about flipping it over. So I can assume the line's going down. The line's going down, it will just go down, sideways, down, sideways, down, sideways, and it will at most be able to go through like one winding path like this, right? You won't be able to ever U-turn back. So here, figure 1, there's 3, figure 2, there's 5, and then here there's 7. So it is quite obvious that these are just your odd numbers, right? So 3, 5, 7, this is for a 2x2, this is a 3x3, this is a 4x4. So the easiest way to calculate it is that this is 2 plus 2 minus 1, 3 plus 3 minus 1, 4 plus 4 minus 1. So the 10x10 grid should be 10 plus 10 minus 1, which is 19. That was not too bad after all. and we didn't actually need to draw the 10 by 10. We can already see that, oh, that same staircase will happen if I draw it for the 10 by 10, and it saves me the time of actually drawing the 10 by 10. Right, question 28. In the following square ABCD, the length of each side is 50 centimeters. The points EFGH lie on the sides of the square. AEF and BGH are both equilateral triangles. Okay, this is important. Now, there are lots of ways that you can just draw triangles, but equilateral triangles, there's really only one. Right? There's only one way from the corner. It must be symmetric. Right? So it has to be that AF and AE are the same. Right? So these two have to be the same. And so therefore this line AC would be a line of symmetry for that equilateral triangle. Okay, they asked me to find the shaded area. The shaded area here looks a little suspicious, don't you think? It looks kind of like a 90-degree angle. It looks like it. I dare not say it is yet, but we certainly could track it down, right? Maybe it is, maybe it isn't. Now I'll write down what angles I can find first. Apart from the 60 degrees here, what else can I do? Well, since it's symmetric, at least I can say that this angle here and this angle here must be the same, right? Because AC was the line of symmetry just now. I erased it so that it won't be too messy. So 90 minus 60 is 30, and 30 would be split into 15 and 15. If this is 15 degrees, okay, I can move this over to the big triangle. The big triangle would be ADF is a good place to look at, because that's a right angled triangle. So if I have a 15 degrees here, I can move a 75 degrees all the way to the top. And if that's a 75 degrees, then this is 60. 180 minus 60 minus 75 is 45. Great. So this is 45. And then the whole thing is symmetric, right? Because you have two equilateral triangles in a square. So this is also 45. And then this is 90. So this is really a right angle. And oh yeah, and better still, because this is symmetric, it means that the other two angles must both be 45 degrees. Remember, everything in this figure must be symmetric, right? You can just flip it over and everything on the left and right must be the same. So we know how that this 90 degrees, 45 degrees and 45 degrees can be very useful, is because that is basically a right angle isosceles triangle, and the side is 50 cm, means that this is also 50 cm. So all I need is the height, and if I want the height, I can draw it down here. This would also be 45 degrees, so that would also be isosceles, and isosceles, which means that 50 would be split into 25, 25 and 25 here as well. Great, so 25 cm there, the whole area would become half times 25 times 50, which is 25 times 25, that is 625 cm squared. Pretty nice. Okay, how much time am I at? I am at 33 over minutes. Okay, so I should get moving. Question 29. A 6063 digit number n is 6AB, 6AB, 6AB. This is funny. Where A and B represent different digits. If n is a multiple of 77, find the sum of all possible two-digit numbers AB. Okay, this is a little bit sneaky, because it does require you to know a little bit of special property of your prime numbers. Okay, so 77 is no divisibility test for 77, but I can split this into 7 times 11. So I just need to make sure that n is a multiple of 7 and a multiple of 11. Now you may be tempted to say that let's use the test for 11, which will be perfectly good, but there's no use unless we figure out also what to do with 7, which is not something that we have a test for. But if you recognize this, and this is a number that is very common, 7 times 11 times 13 is 1001. Right? And here you have 7 and 11. Now 1001 is a nice looking number, but the reason why it is particularly nice is that when you multiply something like 101, 1001, 10001 to a number, it basically repeats it. Right? So if let's say that you did, for example, right, if you did 258 times 1001, you would get 258,000 and 258. So you have 258 repeating. If you did, let's say 123 times 1001, you would get 123, 123. So that means that when you see a repeating unit like this, 6AB, 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 6AB would be just 1001 times the 3-digit number 6AB. And that means that when you do your hypothetical long division, each of these portions of 6 digits, this would be divisible by 1001, which means that it is divisible by 7 and 11, because 7 is a factor and 11 is a factor. 7 times 11 times 13 is 1001. So that means that every 6 digits will just disappear when you're dividing. And so when you divide off using your long division, right, so n is a multiple, not divided by 6063, what am I writing? When n divided by 77, it would be all gone except for, since 6063 gives you 3 more at the end, there are 21 blocks of 3. So the last block of 3 will give you 6AB divided by 77. Everything else will disappear in your long division. And so all you need is a multiple of 77 that starts with 6. 77 times 10 is 770. You minus 77, you get 693. You minus away 77 again. From that, you get 616. And that's it. So 93 and 16 are the only 2 3-digit numbers you can get. It adds up to 109. Yeah, once in a while we get tempted to say, that's not fair, how am I supposed to figure this out? Well, I would like to think of it as, these math competitions really are meant as a reward for people that love math. Right? So for me, I love to do math. I used to just list out number patterns. Right? I just like to look at numbers and look for special things about them. And when you do that a lot, you start to notice special things about every single whole number. And this kind of question rewards that a little bit, because you remember that there is this special thing, 7 times 11 times 13, 1001, and 1001 times any 3-digit number just repeats it. And that will help you to solve the question. Right? So rather than get a bit too frustrated and feel that, that's not fair, I wouldn't have thought of that, think of it as this is a reward for people who think about math very often. Right? Outside of school, outside of lessons, just enjoying exploring numbers, which have lots of amazing properties. Okay, that's the mathematician in me coming out, because I love numbers very much. But let's get back to our task on the last question. A railway network is set among 5 cities, refer to the diagram below. The network consists of 7 straight paths which are 2-directional and 2 curved paths which are one-way in the anti-clockwise direction only. Okay, so clockwise and anti-clockwise. I want to use my finger, but I'm not sure how the video mirrors my body language, so I think I better not. I'm just going to draw it. So anti-clockwise would be here and here. Right, so it says in the question from B to D or D to A only. That's silly me. The local tourism board wants to design a sightseeing route starting from A, passing through each city exactly once and coming back to A. For example, A, B, C, D, E and back to A is one such route. How many such sightseeing routes are there in total? I don't think there's something too clever that you can do, but there are only 5 cities, right? And you must start and end from A. So it's basically A to 4 other cities and back to A. Now you know that B, C, D, E, if you were to arrange them, is only 4 factorial, which is 24. That's already not many. And this answer therefore will be much less than 24 because there are lots of one-way routes and then B and D are not connected. So it can't be that many. Let's just see how it goes. Well, there are 2 places where you can start from, A. So A could go to B, or A could go to E first. So let's do them one by one. If let's say you go from A to B, from B you can go to anywhere. So you could go C, D, E and back to A, that's what the question suggests. You can go to C, E and D and back to A. That's it for C. So you can also from B go straight to E. So if from B you go to E first, then from E you can't go DC, you must go CD back to A. And that's all, right? A, B, you can only go to, oh, you can go to D first, yeah, I forgot. So, yeah, so for A, B, you can go to D. Yeah, I almost forgot about this one on there. So A, B, D, and then from D, you can go to C, E, A. You can't go to EC because you from C you can't get back to A. Yeah, so that's definitely it for the ABs. Now let's try if we went down AE first. Now AE, if you went AEB, then B must go to D, D, then you're stuck, right? You cannot get to C and back to A. So that doesn't work. From E you could go to C. So C you could have BDA. You can't go from D back to B, so that's all for C. So I've tried B, I've tried C, now I can do D. Oh, I think I missed something, didn't I? Let me think. Now let's, oh yeah, I forgot, right? If you go from E to D, no, D is the one that we already, okay, now D you can go to CBA, and then yeah, B just now, why did I jump over B, right? AEB you can go to CD and A. Okay, did I miss anything? Yeah, I'm confusing myself a little bit, but this is really quite simple. I'm just listing out in order. Right, from E I can go to B, then I check whether it works. I can go to C, I check whether it works. I can go to D, I check whether it works. B, C, D, A, C, B, D, A, and E, D, C, B, A. Yeah, so that's it, I think. And yeah, it's just 7 ways. This is not very clever, but I don't think you need anything more clever than that. Okay, and this video has just gone past 40 minutes, so we should wrap up here. Hope that it does show that it is theoretically possible to go through these 30 questions in 90 minutes without all my additional comments. I hope you find this interesting as well. Right? Some of you are not taking the NMOS, or maybe you are already too old to take the NMOS. But these sorts of questions are also useful for other competitions, the AMC 8 for example, and some other P6 contests that you might be doing have similar types of questions as well. Okay, so thanks everyone for watching. Leave a comment below if you have any suggestions, any comments, any requests, or as usual, if you think you have a better solution to any of these questions, please do mention them below and it would be of help to anyone else that's watching the video. So thanks for watching again, and see you again during the next review of another contest. I think I'll be doing AMC 8 next time, so do look out for that. So bye for now, see you again.